Hey guys, Physics in the Flesh is back with another Law of Universal Gravitation problem. Calculate the effective value of g, the acceleration of gravity at A, 3,100 meters above the Earth's surface, and B, 3,100 kilometers above the Earth's surface. Okay, so this is the problem we're dealing with here. Generally speaking, let's say this is the Earth, there's our person. Clearly the diagram's not to scale, but that's okay. For the purposes of our problem and our solution, it'll be fine. Okay, so here's the radius of the Earth. Now, at this distance from the Earth's center, acceleration due to gravity g is about 9.8 meters per second squared. And for most problems we do, this number is a pretty good estimate because if you're just a little bit, couple meters above, it really doesn't change by enough to make a significant difference in your final answer. So in this question, we want to see, well, if we did want to consider it, how much does it change if you're 3,100 meters above the surface? So if you're about here, let's say that's 3,100 meters. And well, what if you're 3,100 kilometers? So what if you're much further? Again, this is clearly not the scale, but just to show you, relatively speaking, what's going to be the difference between the force of gravity up here versus way up here. So that's what we're looking for here. The first thing we have to do, we're looking for the value of g, so we need an expression to help us determine that. Now, so far, when we look at the force of gravity, we know two different formulas for the force of gravity. We know that on Earth, we can say that Fg is equal to mg because we know we're dealing with a certain object. So the acceleration due to gravity g is the number targeted just for that body. So for Earth, we say 9.8. You plug in the mass of your object. Now, the law of universal gravitation tells us that to find the force of gravity between any two masses, you use this formula. You use the capital G, the universal gravitational constant, times the mass of one object times the mass of the other object divided by the distance between them squared. Now, if I'm looking for the acceleration due to gravity, all I'm going to do is have to equate these two equations, and I'm going to determine how to make an expression for g. Okay, so if I say, you know what, let's equate these two equations, because after all, force of gravity is force of gravity, right? We can set them equal to each other. mg equals gmm over r squared. Now, some formulas call this M1, M2. You can call it lowercase m, capital M. All that really matters here is that one of those masses cancel, and you're left with G is equal to capital GM over R squared. What you need to make distinct to yourself and aware is, what is this M? Is this the mass of the satellite or the mass of the host object? Okay, so think back to this formula. The little mass here, that's not the mass of the Earth. That's not the mass of the host object. That's the mass of the object relative to the Earth, like how is it affected by the Earth's gravity? Okay, so that little mass we canceled out, that's the small mass, the satellite mass, let's say. This capital M, this is the host object's mass. Okay, so don't mix that up. So if you're looking for acceleration due to gravity of the sun, you plug in the sun's mass here. Okay, so at this point, I mean, we've got our formula, we just have to plug it in. So you know what, let's go ahead and do that. So for part A, we have to find the acceleration due to gravity at a distance of 3,100 meters above the Earth's surface. Now, before you just go ahead and start plugging in numbers, don't just plug in 3,100 because, remember, r is the distance between the center of the objects. So go back to your picture. Let's say your object is here at 3,100 meters above the surface of the Earth. The distance between that object and the center of the Earth is this total distance right there. That's the radius of the Earth plus the 3,100. And you're going to do the same thing for the 3,100 kilometers. Okay, it's the radius of the Earth plus that. Now, they don't tell you the radius of the Earth in the question. It's assumed that you know it, and if you don't, you should memorize it. The radius of the Earth is 6.38 times 10 to the 6 meters. Okay, so just memorize that. You might be given it on a formula sheet. I don't know. Make sure you check on that. Okay, so here we go. That's the distance above the surface, but the radius that we're going to plug in, so let's put it as r star is equal to radius of the Earth plus r. Okay, so let's plug in our values here. The acceleration due to gravity for part A is equal to gm over r star squared. So g, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared times mass. Mass is the mass of the host object. So here we're going to do mass of the Earth Again, something you may have to memorize, and if you haven't memorized it, mass of the Earth is 5.97 times 10 to the 24 kilograms. Okay, so 5.97 times 10 to the 24 kilograms divided by r squared. Now my r is going to be 6.38 times 10 to the 6 meters plus 3,100 meters, and that entire thing gets squared. When you plug all this into your calculator, you are going to get that the acceleration due to gravity is 9.77 meters per second squared. And that answer makes sense. It's just a little bit below 9.8, and you're just a little bit above the Earth's surface, 3,100 meters. It really doesn't make that much of a difference in the number. Okay, so now part B, we're 3,100 kilometers above the surface. Okay, so GB is equal to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times the mass of the Earth, same thing, 5.97 times 10 to the 24 kilograms divided by the distance squared. So again, it's the radius of the Earth plus that extra distance, 6.38 times 10 to the 6 meters plus, now 3,100 kilometers, how do you write that in scientific notation? 3,100 kilometers, it's technically 3,100 times 1,000 meters, right? Because to go from kilometers to meters, you multiply by 1,000. Okay, if you want to express that in scientific notation, it's going to be 3.1 times 10 to the 6. So just double check that. If you go 1, 2, 3, and then another 1, 2, 3, you make up for the 1,000. So 3.1 times 10 to the 6 meters. So you can already see now both of these numbers are on the order of 10 to the 6. It's going to have a much different effect now. And you square that number. When you plug all this into your calculator, you are going to get GB equals 4.43 times, actually just 4.43. 4.43 meters per second squared. And you can see that's pretty much half of the actual acceleration due to gravity at the Earth's surface. So if you travel far enough, it does decrease. Otherwise, it pretty much stays the same. So that's it for this video, guys. I'm going to encourage you once again to please click that like button so that I know if you learned something from this video, and subscribe to Physics in the Flesh so you never miss a video from me. Stay tuned tomorrow at 12 noon to see Law of Universal Gravitation video 3.